SUVAT equations applications. So this is a continuation of the previous video on the SUVAT equations, how I derive them. So the SUVAT equations, to remind you, are the following. You've got V equals U plus AT. You've got S equals UT plus half AT squared. And you have V squared is U squared plus 2AS. Remember, SUVAT is like an acronym. S is displacement, U is initial velocity, V is final velocity, A is acceleration, and T is time. Let's see how these things work. Okay, let's start with the following example. Suppose, I'm going to keep this short, speed of a car increases from 5 meters per second to 15 meters per second in 2 seconds. What's the car's average acceleration? So let's calculate this. Before we do that, I always say to my students, you always follow this recipe. You always begin with what you know. You'd never rush into solving. Now, let's dissect this. Increases from this to this. If it increases, it means that this, the 15, that is our final velocity V. And our initial velocity is U. Because initially it's 5, increases to 15. 2 seconds, that's our time T. Average acceleration, that is A average. That's what we need. So that's what we know. What do we need to work out acceleration? Well, we're given velocities, 2 velocities, U and V, and time. We know that average velocity is just the rate of change of velocity over time. Delta V over delta T. Delta V is just final minus initial velocity. So V is final minus U initial over the change in time. Now the change in time in this case is just 2 seconds. V, that's 15. U is 5. So 15 minus 5 over 2. 15 minus 5 is 10. 10 over 2 is 5. So the average acceleration is 5 meters per second squared. The units for acceleration. This is a typical 2-mark question. 1 mark for the working out, 1 mark for the answer. Now you must have units in your answer. If you don't have any units in your answer, that's half a mark lost. So that's the first example. Second example. Suppose there's a cruise ship that accelerates at a constant rate for 10 minutes until it reaches a speed of 10 meters per second. And it then continues in a straight line for 20 minutes at 10 meters per second. Number 1, so part A, part 1 for question 2. Sketch speed versus time graph. So speed in meters per second and time in seconds, okay, for the 30 minutes that the ship is moving in. And part 2 is to calculate the ship's acceleration in the first 10 minutes. And part 3 is to sketch an acceleration versus time graph for the 30 minutes the ship is traveling at. Okay, let's dissect, let's unpack all of this. It's really not that hard if you think about it. Okay, so we need to draw a graph, sketch a speed versus time graph for 30 minutes. That's part 1. Zoom out a bit. Part 1. Okay, so time is always 99% of the time in physics on the x-axis, t, and it says seconds. Okay, you've got to put your units there as well. Speed is v, measured in meters per second. Okay, now we need to convert. I've got an issue here because it says 30 minutes, okay, but it's got to be in seconds. To go from 30 minutes to seconds, you've got to multiply that by 60. there are 600 seconds in 30 minutes. So the x-axis here for time, 600. Okay, let's go up by 600. Then you get 1200. Then you get 1800. Now, the speed, it says here at the very top, it's going at 10 meters per second. Okay, for the first 10 minutes, it's going at 10 meters per second. Then it continues for another 20 minutes, 10 meters per second. It says it right there. So it's traveling at 10 meters per second for the 30 minutes, okay? Because 10 minutes plus 20 minutes is 30 minutes. So that speed there is 10 meters per second. So for the first 30 minutes, the first 600 seconds, it's traveling at constant speed. I should say for the first 10 minutes, constant rate, that means it looks like that. I should say it's a line, it's a linear trend, because if it accelerates, acceleration means the rate of change in velocity. So there's a delta, acceleration is delta V over delta T. It's got to be a line like this, not a flat line. A flat line at 10 meters per second indicates there's no acceleration. It's going at constant speed, but it's not going at constant speed. It's accelerating. And then it continues in a straight line for 20 minutes at 10 meters per second. So in other words, the velocity, the speed is constant. It's a flat line for the remainder of the time, okay? 1800 seconds, that's how many seconds there are in 30 minutes. So that's part A, part one. Part two, we need to calculate the ship's acceleration in the first 10 minutes. Acceleration is the rate of change of velocity over time. That's just final velocity minus initial velocity over t. Now the final velocity is 10, initial velocity is 0. Okay, initially it's right there, it's 0. So 10 minus 0 over 10 minutes. However, we need seconds, okay, because meters, that's meters per second. We need seconds, time in seconds, so we multiply that by 60. So we get 10 over 600, and that'll give us 1.67 times 10 to the minus 2 meters per second squared. That's our acceleration for the first 10 minutes. And then part three, we need to draw an acceleration versus time graph for the 30 minutes. Now, the 30 minutes, the x-axis doesn't change. Okay, so it's still 600, 1200, 1800. Acceleration's up here. They're the units, meters per second squared. Okay, how do we draw a graph of this? Now, let's look at 0 seconds to 600 seconds. What's happening here? It's accelerating. It's accelerating at a constant rate. So that linear trend there will give a flat line. Okay, for the acceleration, 1.67 times 10 to the minus 2. That number there. Okay, for the first 600 seconds, that's the acceleration. So it's a flat line. Then here, it moves at constant speed for the remainder of the time. Okay, for 20 minutes after that. A flat line, constant speed means there's no acceleration. So it jumps straight down at the 600 mark, all the way to 0. And that's your acceleration time graph.